Hello everyone, my name is Grayson Duggar, and this is Physics 2212 Lab 2, Lines of Charge. The purpose of this lab is to determine the excess charge on tape and how it interacts with other objects, as well as using a computational model to simulate the interaction between the charged tapes. In this lab, we use the principles of Newton's second law of motion and Coulomb's law. The main result of this lab is that the charged tapes were electron deficient, meaning they were positively charged and repelled one another. The magnitude of the electrical forces was the same as that of Lab 1, but the electrical charge of the tape itself was vastly different from that of Lab 1. Newton's second law of motion is a formula used to relate the mass and acceleration of an object to the force being applied on it, or F equals ma. Coulomb's law is a force used to show electrical force of one charged object upon another, and it is force equals K, which is a constant, times the charge of one, times the charge of another object, times the position vector. In our calculations, we are modeling the charges on each tape as a line charge spanning the length of the tape. This is different from Lab 1, where we used a point charge. We do this to give an accurate estimation of the charge of the tape. We are also assuming in these calculations that air resistance is being ignored. This allows for simpler calculations with regards to finding gravitational force. Also, each U-tape had about the same amount of charge, evenly distributed along the length of the tape. This enables us to find the charge of both tapes by finding the charge of just one. The following is background on the physical experimentation of Lab 1, as it is also used in the calculations of Lab 2. In our experiment, the system is the two pieces of tape, and the surroundings is everything else in the universe. The floating tape dimensions are 0.254 meters by 0.0254 meters, and its mass is 0.000254 kilograms. The distance of the floating tape away from the other piece of tape is 0.017 meters. Gravitational force is 0.00249 newtons downwards, because the direction of gravitational force points down. The electrical force is the opposite of this, 0.00249 newtons upwards. This is because the acceleration of the tape is zero, so the overall net force of the tape is zero. And since the two forces acting on the tape are gravitational and electrical has to be the opposite direction of gravitational. In this code, we modified a given starter code to model the tape as a line charge with many different smaller sections, and then summed up the parts to get the overall charge of the tape by estimating this charge until the magnitude of electrical force and gravitational force were the same. The result, as far as the actual charge goes that we estimated, is vastly different from the results of charge that we obtained in Lab 1. Some possible sources of error in this lab are error when measuring distances between the tapes, as well as the tape's dimensions. Also, the amount of charge on each tape is likely not the same. As for our what if and what does it mean questions, what if you had modeled each of your tapes as a single point charge, like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge to the value you get with your line charge model. When modeled as a point charge, the charge of the point was 8.94 times 10 to the negative 9 coulombs, whereas the charge as a line charge model was 1.457 times 10 to the negative 8 coulombs. As you can see, there is a very great discrepancy between these two numbers. Why do these estimates differ? Which value is more likely to be closer to the real value, and why? These estimates differ because they use vastly different methods of calculating the charge of the tapes. The line charge is likely more accurate, as it uses a closer, more realistic approach and model to calculating the charge of the tape. In conclusion, we used this lab to model the effects of electrical force on objects in real life and created a computational model to help further visualize this phenomena. If you have watched this far into the video, have a nice day and good luck to you in the rest of this class.